4 of our very long lecture about wakes. Now, as I told you, in your book there's like 3 main sections. There's the part about turbine-to-turbine wakes, which is everything we've seen so far. And then there's 2 short sections about wind farms and inter-wind farm wakes. Now, the book also does talk a little bit about like equipment for measuring wakes and so on. You know what, we've spent plenty of time on equipment in this semester. We don't need to bog ourselves down with that again. But it probably is worthwhile to talk about wind farms. I mean, we've talked about wakes, and we've kind of scared ourselves a little bit. I mean, look at all these wakes. I mean, look at all these turbines in here. Holy smokes, look at this one over here on the sides of this hill. I mean, there are just so many turbines, and every turbine costs a lot of money to build, and yet we work so hard to site these turbines and to do our meteorological studies and our climatological studies before we actually chose this site so that we'd have the maximum wind, and then we put these turbines up in the wakes of other turbines, and they end up having less power. And, you know, even at the ocean, where in theory we would have a lot of space to do these things, we're still under constraints as to how far apart we can put these turbines and how big an area is it cost effective to put the turbines in. Like, maybe there's an area where the ocean's a little shallower versus it's deeper. It's going to cost too much to put the turbines in where the water's deep. Oh man, we end up putting them all so close that they gotta be causing trouble for each other with their wakes. And that tends to be the way we build wind turbines. I mean, don't get me wrong, you sometimes see an isolated single wind turbine that maybe a city has or a factory or something like that. But by and large, we tend to see them in the form of farms, where there's, you know, a few dozen farms, a few dozen turbines in a relatively small area. Why? That seems so stupid when you think about it. I mean, we got all these wakes. Every turbine we put up just gets less power and causes wakes for the other turbines. I mean, it just seems like this can't possibly be a good idea. Well, hopefully you can already think through and think, wait, we wouldn't build them that way if that was a bad idea. There must be something we're not seeing. And that's because it's about the scale of this. Let me show you what I'm talking about. Here is a lovely map of a wind farm known as Bigelow Canyon. Bigelow Canyon is in Oregon, and it's a relatively large wind power facility. You can see I have a nice map of it right there that I found someplace on Wikimedia or something like that. And there's a few dozen wind turbines at Bigelow Canyon. Now, every one of those turbines is indicated there where those circles are. I don't want you to get the idea that like the circle is the turbine, though. The center of the circle is where the turbine is, but the circle itself there is about 800 meters across, I believe is what it says. I'm sorry, I had a hard time reading that for a second. I mean, it's a pretty crowded place. If you actually look at that picture, that's a picture from when they were building one of the turbines at Bigelow Canyon. I mean, those turbines almost look like they're hitting each other, but they're not. Those circles that are on there on that diagram there are 800 meters in radius. So, I mean, even if these were 50-meter blades with 100-meter long diameters to these turbines are actually not that big compared to those circles that you're seeing on there. So if those circles are like an 800-meter radius, and the blades of your turbine are like 50 meters long, these turbines are not all that close to each other. And, well, 800 meters is actually pretty far. I mean, that would be 8 rotor diameters downwind. And if we just take a look, for example, from our N-O-Jensen model as to how much the wind speed should be reduced 8 rotor diameters downwind, that's the spot there I have marked on the curve from N-O-Jensen's downwind wind speed on there. Well, the environmental wind was 10 meters per second in that example, and we have a wind speed now of right around 9 meters per second, 800 meters downwind. I mean, we just don't have that huge of a reduction of the wind speed, even as little as 800 meters downwind. So most of the time, this just isn't really a big problem. Now, I had a lot of fun in PowerPoint. What I did here is I took those locations of all those turbines here at Bigelow Canyon, and I have made a little illustration to show like which way I want the wakes going. So like I have a big wind here out of like the south-southwest or something like that, and I pointed all the wakes to be going upwind. And you can see that, in fact, in this example, and I made them fairly realistic, I have them extending a little bit more, see how they get wider as they go away from the turbine, and I have them go a little bit farther than 800 meters downwind, so they're going about 10 rotor diameters downwind. And I just wanted to show you here, like at this south-southwest direction of the wind, literally not one of those wakes is actually hitting a nearby turbine. We're not affecting the power of each other one of them at all. Oh, we have no problem with wakes here. Oh, huh. Well, what if I tried a different wind direction? So I played with this for a while in PowerPoint, had fun, and like I tried this direction. This is kind of a east-northeast wind. And, well, if you actually look here, sometimes some of these turbines are inside of the wakes of others. I mean, if I just zoom in on one cluster of them right there, you can see how the turbine that's sort of in a blue box right there is at that direction in the wake of turbine 7, apparently. Okay, I mean, it's still more than 8 rotor diameters away. The wind speeds are not being reduced by a lot, maybe no more than a meter per second or something like that. But in fairness, the power being collected by the turbine is due to the flux of kinetic energy, which is proportional to the cube of the winds, as we learned way back in Module 1. So even a 1 meter per second, I mean, we're affecting the amount of power that turbine there is collecting quite a bit. Quite a bit. Okay, so we're going to have to make some calculations here to actually figure out, does it make sense to build that other turbine? So here's what you would have to do. You would have to actually set up a diagram like this one that I took from your text, where you are showing how much overlap there is between the wake of the upstream turbine and the radius, the cross-section, the rotor of the downwind turbine. So this diagram isn't very well to scale, but you get the idea that as the wind goes from left to right across the page, you have a turbine that is creating a wake. You use the Enno-Jensen model to figure out how wide the wake is and how much area it overlaps of the downwind turbine. You'd have to know its speed. And then you could use the wind rows from like what we saw earlier in the semester, based on your climatological and meteorological studies of the location, to know how often is that direction going to happen. And so then you could actually figure out the economics of, does it make sense to build a turbine at this second location? And the truth of the matter is, it's almost certainly going to be yes, because the truth of the matter is the wind isn't going to be from that specific direction all that long, and the turbine is probably far enough away that the total reduction in the wind speed isn't that much. Then unless we're talking a huge number of overlapping wakes, this is just not going to be likely to be a problem for your wind farm. Real quick, then why do wind farms look so crowded? I mean, if these turbines really are far enough apart that, like at Bigelow Canyon we saw on that map, well, if those circles that were on the map were 8 rotor diameters anyway, how come when they take a picture, it looks like these rotors are almost touching each other? And when you see pictures of wind farms, it often looks like these rotors are side by side or very close to each other. And the answer is, it's kind of a photographic trick. Okay, when you take a photograph of a turbine, if you are close to the wind farm, you're going to have a picture that has one really big turbine right in front of you and everything else is pretty far away and looks really small. And that usually isn't the image you're trying to capture. Generally speaking, those kinds of pictures of a wind farm are taken from fairly far away, like by an aircraft or on a balloon or something like that, with a very long focal length on the picture so that you can see lots of the turbines, but that gives you the illusion that they're close to each other and all, you know, they all look they're about the same size. Well, that's just because they're so far away, right? They're all about, you know, you can't tell the fact that some of them are closer and a little bit bigger when they're all so far away on the picture with that long focal length. So the picture makes them look like they're closer together than they really are. When you actually see a wind farm on the ground, it's clear these are far enough apart. Well, I mean, actually that makes perfectly good sense, right? They wouldn't waste millions and millions of dollars building the wind farm if the turbines were too close to each other and were affecting each other's power production excessively, right? All that's been talking about was a wind farm, a wind farm. Let's talk about how one wind farm affects another wind farm that may be some kilometers away, so-called inter-wind farm wakes. This isn't the wake of a single windmill or wind turbine. This is the wake of the entire farm itself. The entire collection, the ensemble of all of these turbines together makes an effect on the wind, and their wonder if the wind, if that effect propagates downwind. Is there a reduction in the wind speed downwind due to the whole wind farm? Not just each individual turbine, but collectively as the whole wind farm. I mean, this isn't as naive of an idea as it might sound. See, here's the deal. When you build a wind farm, a whole lot of factors go into the decision as to where to put it. And not all of them are about the meteorology. And whatever decisions you reached about where to build a wind farm, odds are that's also, places nearby are also good places to build a wind farm. As a consequence, it's commonly the case that once one wind farm has been built in an area, it's commonly the case that nearby other companies will build wind farms, or your company will build more wind farms, within a matter of kilometers or something, maybe tens of kilometers from your existing location. That's not really a coincidence. I mean, it makes some measure of sense. There are a lot of reasons why once one wind farm is there, it becomes a advantageous reason to build more wind farms there. Like, some company has apparently spent a bunch of resources already to increase access to the power grid, to be putting that green renewable energy into the grid. That first company has already cleared all the environmental approval processes by the necessary regulatory agencies and so on, so it can be done. If you meet the same standards they met, you'll get approved too. If public opinion is supportive of one wind farm in that location, they're probably supportive of another. There can be difficulties associated with construction that make one location favorable. For example, for an offshore wind farm, there might be a place where the ocean is not very deep, where the floor of the ocean is shoaled, and it's just relatively cheap to build your offshore wind farm here versus someplace in deeper water. Access to personnel. There's lots of reasons why once one wind farm is built, it kind of draws other wind farms to the same area. And as a consequence then, while each individual turbine is creating a wake locally, the whole farm is creating a wake in the flow too. A reduction that might not be all that much, maybe we're talking on the order of like a meter per second, but it's not just a few tens of meters wide. This could be kilometers wide that you are reducing the speed of the wind downwind. As it happens, these kinds of wakes that are created by the whole wind farm do appear to exist, and they're wider and potentially harder to dissipate than the wake of a single turbine. As they get wider and deeper, being created by a large ensemble of turbines, there are effects about like static stability and so on that are coming into play that make these harder to dissipate. They're going to propagate farther downstream than like the wake of a single turbine. Kind of in the same way that like the smoke from a single campfire propagates a certain distance downstream, but if you had an entire forest fire, that smoke might propagate very far downstream, right? Okay, there can be an effect that goes much farther just because there's a change in the scale here. And this, of course, has the potential to complicate the economics of whatever turbine a wind farm is downwind greatly. I mean, if you built your wind farm first, and you were building it around a certain economic model, you needed certain wind speeds and so on, a certain fraction of the time and so on, and then somebody else comes and builds a wind farm that a certain amount of the time is upwind of you, they've just messed with your economics of this, right? I mean, a reduction of the wind speed of 1 meter per second integrated across many turbines could be a very large change in the total amount of power that you're producing from your wind farm. All of that is a very complicated idea that is very much an area of active research right now. In general, the effect of the collective effect of a wind farm is a very hot area of topic in atmospheric sciences and energy technology and so on right now. To some extent, the effect of a single turbine has been sort of studied to death, but the ensemble effect of a whole collection of these turbines is something that is actually quite an interesting topic. In fact, a few years ago there was research going on at Creighton that was about things like how a wind farm affects the production of clouds. This could potentially be quite an interesting idea. If your wind farm was changing the distribution of cloudiness, like let's just say making it less cloudy during the day, well, if your wind farm was producing clean power, but it was increasing the amount of hours of daylight and you needed more air conditioning to cool the homes in that area with less clouds, Maybe the wind farm wasn't such a good idea. There's a lot of these kinds of sneaky, complicated ideas once you start wondering how a whole wind farm starts affecting the environment. Fortunately, that's kind of outside the scope of our class. This is not the macro scale issues of renewable energy and environmental issues and so on. We can just take this and answer 2 more quick questions and be done with this lecture. Question 13. Suppose there's a wind turbine at some location, and the only site where you can get permission to build a second turbine is 1 kilometer away. Should you build it, or will the wake of the original turbine affect the second one too much? A, it'll be fine. A kilometer is about 10 rotor diameters, which is far enough away that we don't need to worry about the wake of the original turbine. B, the second turbine will not generate any power when the wind flows from the first to the second windmill, so we need the windrows in order to answer this question. You don't need to know how often the wind is blowing in that direction. Or C, don't do it. 1 kilometer is too close and the wake will always be a problem. Alright, which of those 3 is the right answer to whether or not we should build that second turbine? Make a choice from those 3 options, get a little feedback before you move on to the final question in this lecture.